Okay, so I heard from some students that the auto grading of the quiz cannot recognize the diversity of different kind of answers, right? Like you have a unit, but the correct answer doesn't have a unit, for example. Okay, so if that happens, then basically you get the right answer, but the format is not correct. Please contact the TAs. Okay, the TA will check your answer. And if it's truly correct, the TA will approve another attempt. Okay. We will wait for 2 more minutes, and then we'll begin. Right. Okay, just to make sure, so you can see the slide, right? Just want to make sure. Anyone can give me an answer, just to confirm that you can see the slide.
Yeah.
Okay, thank you. Okay, let's begin. All right, so I think students are still joining, but let's start by reviewing what we have covered last time. Right. So this is the second slide on the data link layer. Right, the previous one is more basic stuff like how to delineate frames. Okay, this one is more on the media access. Okay, so why do we need a media access? Because a lot of the time, especially in your local area, right, network. So a lot of the time you are connecting to the same media. Okay, like multiple laptops in a classroom that are connected to the same, wireless router in the classroom. Okay, so in this case, basically everyone is broadcasting your signal into the air, right? So for example, if two people are sending together a packet, okay, then let's say if you are sending 1 bit, the other person is sending 0 bit. But when they reach together to the wireless router, the router will only get 1 bit, right? Because it's a high signal. So that will be so-called collision. Okay, so this is what we were talking about earlier. Right, so we covered this a little bit, okay? And this will destroy the data content, okay? So one each time, okay, 1 packet each time, this is necessary, right? So how to guarantee this? So we have the MAC protocols to do this, okay? So, oh, just one more, I might have to temporarily leave for 2 minutes. I will be back very soon. Sorry for the interrupt. Yeah. Okay. Yeah, I'm back. Okay. So we needed the MAC protocols. Okay. So so there are rules basically everyone is following on how to share the media. And so mainly these protocols are telling each host how to detect that other people are sending signals and how to avoid sending and how to recover from collisions. Okay, for example, detecting is saying whether someone is already sending something on the wire. If that's the case, I don't need to send. But if I send, I will corrupt the signal. Okay, avoid. So you first detect. If you detect it, you avoid that. Okay, and also you want to recover from the collision, which means if you somehow you send and then you detect other people are also sending, right? So your message is corrupted and not delivered. Okay, then you need to retransmit, right? And you cannot retransmit by, for example, sleep for 2 seconds and send again. Okay, the reason is very simple. You think about it. Everyone that, let's say, two hosts both detect the issue, okay, and then they both sleep for 2 seconds and send again. So they will collide again, okay? So we need to have some randomization strategy to handle that, right? So there are different strategies for media access. And so the first group is called a channel partition, right? So we talked about we can use a time division multiple access, right? So this strategy is something like this. You will, for example, we have 3 machines, okay? So everyone will just use, will take turns to use the bandwidth. Right? So for example, another user will use a second slot, okay? And a third user will use a third slot, okay? So only when your slot comes, you can send, right? So this is actually okay, and actually is the most efficient way if everyone is sending abundant data, right? You always have something to send, right? The bandwidth is always used and there's no overlap, okay? So this is perfect if you always have something to send. But the issue is that most of the time, right? So only a few people are sending in the shared media, right? Okay, maybe you are, maybe we have 100 students connect to a wireless router, but actually only most of people at this point is browsing the website, right, which is already downloaded to your browser, and then 2 more people click and send new requests, right? But for these people, for example, if only one person needs to send, he can only send in these slots, right? These slots, although they are not occupied, you cannot send. Right? So this is the problem with this kind of channel partition method, right? So this is the intuition. So one way is called a time division, right? Time multiple access, TDM. Okay, so this is basically, if we think about this as a time, this is time division, right? So divide the results into small pieces. Okay, right? Each piece is one host. Okay, and another way is called the frequency division, multiple access. Okay, there's also code division, CDMA. Okay, so DMA frequency band is saying that, hey, you actually, your signal have many frequencies, right? So this is a very small frequency, this is a high frequency, okay? But if you can use all the frequency bands, then you can send a lot of data, more bits, right, at each time unit, okay? Let me see if there's a question. Clinton, can you make it clear what you mean by that?
Yeah, I guess the diagram that you draw, there's an arrow going horizontal to this. I wish you could see my cursor.
Yeah.
I'm gonna point to it. I don't know what it is. It looks like an E almost. It's blue.
Oh, yeah. Let me.
What is that referring to?
Okay, so
you just erased it.
Yeah. So basically, one way is that so there are 2 dimensions basically. Okay, let me use black. Okay, so one dimension is time. Okay, another dimension is maybe your bandwidth, your frequency. Okay, the frequency is something like let's say time is t. Would that be okay?
Perfect.
Yeah. So one way is you can, everyone can use all the bandwidth, right? I can use this. Okay, so this is called the time division. But I cannot use other colors bandwidth, right? Another way is actually called the frequency division, which means you can continuously send, but at a lower speed, which means, for example, so let's say one person may use this frequency band, okay, high frequency band. Another person can use a medium frequency band, okay, and the last one can use a low frequency band. right? So you can always send, but your speed, right? How many bits per second? Only 1/3. So this is these are the two different methods. One is TDMA, one is FDMA. Is this okay?
Yeah, that's good.
Okay, yeah. So this is just a illustration of the idea. Okay, and next let's take a look at the second method. Okay, the second method is called take times method. Okay, right. So that means, of course, this is also taking turns, right? But for this take turns method, we have a token. Okay, it's a ring network. Like these hosts are considered in a ring. Okay, these three people, and we pass a token to each person. Whenever you have the token, you can send. If you don't have the token, you don't send. But there's a lot of complication in how to pass the token, right? So make sure at any point only one person has a token. Okay, when the token is passed to you, then you can send. So the mechanism is a little bit different, but the idea is kind of similar to this, right? And of course, if you can hold the token for a longer time, then you can send longer. Right? So it's a little bit different from the channel partitioning. Channel partitioning is like a totally evenly distributed, right? So if you have n users, you can only use 1 by n of the medium bandwidth. Okay, so if you have a lot of users, the performance is really poor. So, but again, if you have a lot of users, they are sending like movies together, uploading a movie, right? So a big file. Okay, that's fine because this is at any point of time, the bandwidth used, and there's nothing, no conflict happens, right? Okay, so this is actually good. So these two methods, token and the channel method, if you have all the users in the same media, right? So connect to the same media, have enough data to send. These are the best. Okay. But the problem is that if you don't have anything to send, right? So you can use other people's slots. Okay, can use other people's small resource pieces. But like channel partition, you cannot do that. Okay, so the contingent method allows that, right? It allows collision, which means if you want to talk, you just talk. And other people may also be talking, but you will detect, okay? And then you use some strategy to recover. I say, hey, when I talk, I also hear other people are talking, then I will back off. I say, hey, you first, right? And then maybe after a small period of time, due to the randomness, right, I see other people will talk first, right? And then like both people say, hey, we are talking together, right? So you first, right? And then someone will first talk, and the other will talk next. Okay, and in this way you avoid this collision again. Okay, of course you should not begin talk after the same period of time. Okay? We will see. So we will wait for a random period of time before we talk again. All right. So examples include like Ethernet. This is a wired connection, right? So you have the wired connection and like an Ethernet switch, and a lot of computers are there. Okay, these days Ethernet switch you don't have this concept. Early on, Ethernet are connected by like hub. Okay, and the old days of technology, it's like everyone is connecting the same piece of metal, and in that case, no two people can send together. These days, with the Ethernet switch, you can send to another people, right, in the same subnet, and A can send to B, C can send to D simultaneously. There's no conflict. That's the difference from hub and switch we discussed later. Okay, and the Wi-Fi is the wireless counterpart, right? So Wi-Fi will need a little bit different strategy. We will see that later, okay? Because Wi-Fi maybe the signal let's say A sends message to B, okay, and C sends message to D, okay, and B may not be able to. B may be far from to the other or the others, okay. Maybe they are sending signal when A is sending to B, but A is interfered, right? But the A's data is already sent to B, and the B's will not be interfered because the signal is too weak by the time the signal reach B from the other sending party. Okay, so we will use some other strategies. We will see that later. Okay, you cannot just think it's the same piece of metal. Okay, so Ethernet, you think everything is light speed, right? So once you put on the wire, other people will find it. Okay, but the Wi-Fi you cannot do that, right? Because the propagation is a little bit slower than light speed, much slower. Okay. All right, so and yeah, so what are the goals of those contention-based protocols, right? So So firstly, so if all these hosts share the same piece of media, right? You think about everyone is connected to the same metal, okay? Then two hosts sending at the same time will collide, right? If you send one, the other guy send 0, maybe everyone will get 1, right? Because 1 is high signal maybe for them, okay? And so this will cause interference, right? And another problem is that if no host is sending, right, the channel will be idle, right? This can happen in the time division case, right? So we talked about this may be 1, this may be 2 time partitions, 3 time partition, 1 again, right? And then after 1 is sending, okay? And now it's 2 and 3 turn to send, but 2 and 3 are just browsing their websites. They are not doing any more action to send. Then these are totally wasted. No one is sending during these 2 time slots, okay? So this channel can be idle if no one is sending. One can send, but one is not allowed to send in 2 and 3 slots, right? Okay. And so we wanna. So our goal is we want one user to be sent at any given time, right? And we wanna, if there's anyone who want to send, they will be able to send until 1. They do not have to wait, okay? Because that will cause latency, right? And but in the meanwhile, so you don't want 2 people to be sending at the same time. Only one user is sending, okay? And when it's allowed that one user can be sending, let the user send, okay? So our goal is really high utilization. As we explained, the TDMA time division method is a low utilization method because when you have a subnet of many students, right? Most of the students may not be like sending new requests, right? They are browsing a website. Maybe you have 50 students, only maybe 10 students are sending new requests at any point of time, okay? But the other 40 students' time slots are still allocated, which is wasteful, okay? So, another goal, right? So the first goal is saying, hey, if we only have a couple of people sending, they should be able to also utilize the other 40 student slots, okay? So this is a high utilization. Another is we want a simple distro algorithm, right? As we said, we have a token passing algorithm, but that's very complicated, right? So it's like a parallel distributed computing kind of. There's a lot of schemes to make sure the token is properly passed, right? And you will not have the time that you hand over the token to the other party. The other party, when he sees the token, right, you should already have not have the token. Okay? Otherwise, you will have collision again because you both will be sent. Okay, so there's some complication and coordination process, right? And another case is maybe multiple hosts cannot directly coordinate, right? So you don't have this mechanism to coordinate. Maybe for the token passing scheme, you need a centralized server, okay, for example, right? So everyone want to request something, will request a token from the server. The server will give the token to that person, and the other one requests the server to, hey, wait for the token, right? When the hosts, after the client host finish using it, will throw the token back to the server. The server can then give the token to the next one, okay? But that's a lot more complicated, and coordination is necessary, okay? Maybe you don't want to have such a dedicated server for the token. Right, so now, so as we said, so the time division and the token passing method are not so desirable, right? So we want to use a contingent protocol, okay? We actually will see 4 contingent protocols. The first is called Aloha, right? Aloha is, hello in Hawaii, right? So, okay, so Aloha, again, here is a shorthand notation, right? So there's a full name. Okay, so Aloha protocol is developed in the 70s for packet radio networks. Okay, we will see what it means, right? So the radio signal propagates much slower than light speed, right? The electronic signal. Okay, and there's also an improved version called a slotted Aloha. Okay, so this means that you start transmission only at fixed time slots. So why this is an improvement? We will see that later. Okay, if you have so the first method is saying, hey, I want to send, I just send. Okay, I don't care about whether there's a slot, right? The second method is say, we still have the slots, time slots for the packet frames. Okay, just like in the time division method. Okay, so I can only send at the beginning of a slot. Okay, if I'm in the middle of a slot, then I want to send, I will have to wait for the next slot's beginning. Okay. So this method will have significantly fewer collisions than the Aloha protocol. Okay. And so we'll see the reason in a later slide. The third method we will look at is called a CSMA, carrier sense multiple sense. Okay, this is for the wild connection because you can really sense on the media, right? So see whether someone is talking. All right, so start transmission only if the channel is idle, right? Because you think about it, this is the same piece of metal. If someone is sending electric signals, you can feel it, right? Then you should not send anything else, okay? Because when you send, other people are also sending. You just corrupt other people's data. That makes no sense. You cannot successfully send your data anyway. Right? So the fourth method is called CSMA, which is the same, right, as here, but CD, which means collision detection. Okay, so this means that we will adopt, collision detection, stop ongoing transmission if collision is detected. This is for the reason that, if you think everyone is in the same piece of metal, right? So maybe you are sending, and when you are sending, other people are also sending, right? So, and then you don't have to finish your packet because maybe the packet takes, let's use a long time, but for simplicity, okay, usually a packet will take a very small piece of time. Let's think you need 10 seconds to send a packet, okay? But after sending for 3 seconds, you find other people are talking, right? So then there's no point to send the rest of the 7 seconds of the packets out, right? Because the packet will be corrupt anyway. You need to retransmit. So you will, whoa, I think someone is drawing. Okay, so if you need to join something, just let me know. Okay. So in this case, you need to stop immediately, right? Because if you continue to send, all the others will not be properly delivered because somebody is also talking, right? After you send for 3 seconds, right? The rest of 7 seconds will be corrupted. So you should stop. The benefit of that, you stop talking, is also benefiting others, right? If you keep sending the 7th for the 7 seconds, other people have to hold, right? Because if they send, then it will corrupt the others. Okay. So these are the 4 variants that we will describe one by one from now on. Okay. So then let's go to the next slide. So the Aloha protocol. Okay. So what's the idea? Right. So as we said, this is really for radio broadcast, right, with multiple stations. Okay. And of course, let's say the B is a receiver. Okay. If A and C are broadcasting simultaneously, you will get nothing. Okay, because it's corrupted. We want A to broadcast its message to B. After that, then C can broadcast message to B can broadcast message to B, right? And if A and C are simultaneously broadcasting message to B, there is a collision. B cannot get the information from either C or A. Okay. So the protocol is for like station transmit data immediately, right? So when you want to send, you just send, okay? But when you send, how do you know that your data is properly received? For example, let's go to here, right? You cannot detect C signal, okay? The reason is very simple. Your C range can only reach B, okay? When the signal propagates to A, it's too weak, okay? So you cannot rely on A to like a carrier sense to understand whether somebody is talking. A can never hear C, right? So this is the case with radio, the wireless case, okay? So the only way is to rely on B, right? B to send acknowledgement to A, right? And if you never receive an acknowledgement, you assume there's a collision, okay? Then you wait for a random time and retransmit. The reason is very simple, right? So for example, if now everyone, A and C after timeout, they didn't get any ACK, right, acknowledgement, they will back off, okay? And then after 2 seconds, if they talk again, they will collide again, right? So that's not desirable. So we will wait for a random time. Maybe I wait for 3 seconds, you wait for 5 seconds, right? Then maybe it will pass through, okay? So that's the reason why we need random. Okay. Any questions about it? Okay, so this method is simple, right? But it's a very radical concept because previous attempts are all using this kind of channel division, like TDMA, FDMA, because there's some guarantee, okay? Right? This method seemingly have no guarantee, right? If you want to talk, you just talk. You don't care about whether there are other people talking, right? So it's very likely some problem will happen. Okay. So this is really, this method, Aloha, is optimized for the common case where you have few senders, just like what I said. Even though you have a lot of people in the classroom, right, at any small time slot, right, it's unlikely many people are sending. Okay, maybe only 10% of people are sending. In that case, we want the 10% of people to also use the other 90% people's slots. Okay, so this is the idea. Okay, so if they just want to talk, it happens as in many times other people are not talking, right? Then you just get things sent. Okay. So the trade-offs with TDMA is we discussed already, right? In TDMA, each host must wait for its turn, right? If you are 1 in 3, right? So you every 3 time steps, you only send one of the slots. Okay. So the delay is also proportional to the number of hosts, right? So if you have 100 hosts, right? So it's like alternating around the 100 people, right? 100 hosts. So in every 100 slots, you can only send once. Okay. Let's say you just finished the previous message, and then your application say, "Hi, I want to send the next message," right? But now you have to wait for maybe 99 slots, and then you send the next one. So the message will be delayed when going out and also coming back. Okay. So Aloha is another protocol where each host sends immediately. Okay, right? So compared with TDMA, if you are lucky, right, you are sending. Okay, then you don't need to be delayed, right? You don't need to wait for 99 slots. Okay, even if there are 100 people, right? Only you are talking in this. You are lucky, right, in this period. Okay, but you can have very low utilization rate because and you need to get acknowledgement. Right? If there's no acknowledgement, that means it's corrupted. Then things are not good. Okay, and TDMA has some guarantee. Aloha, if you have 100 people and maybe 80 of them are always talking, right? So probability that you have some time slots that only you are talking is much lower. In that case, there's almost no utilization. This is like a congestion control, right? And that's why, as we said, like in the network core, the bandwidth is over deployed, right? So it's kind of similar. If you are pretty sure your bandwidth is over deployed, right? Your actual user need bandwidth is much lower than than the available bandwidth. That's fine, okay? Right. Otherwise, if you are almost 80% or 90% full, then the utilization will be very low. Okay? You may always fail. So here is what we call the Aloha, right? Not slotted Aloha, unslotted Aloha. So what will happen is, for example, let's assume that B, let's fix this slot, okay? Let's fix this guy. So B will send this frame anyway, okay? So this time is occupied by B, okay? And then you have another one who want to send A, okay? Of course, you can send a packet like this, right? So you can send a packet like this. There's no collision, okay? Because there's no overlap between the packets. Okay? But if you're unlucky, your starting time shift a little bit to here, right? And then you are here and there's an overlap here, okay? Then it's undesirable, right? But how much window is that, right? So you can move all the way, you think about, move all the way there, right? All the way until here, you still have collision, okay? You still have the collision, okay? So the only solution is, if you don't stand before this period of time, okay? Then the only way that you can successfully send is if you are here after. So that means you either send at this point in time, okay? Because if you send that point, you will collide, okay? Or you send at this point in time, okay? Because before this, you will collide with something, okay? So that means this is 2 frame size, right? Once B is sending, you have to skip these 2 frame size time, okay? So this is why actually we will see this the Aloha has a half utilization rate than slotted Aloha. If you slotted Aloha, you require everyone can only send at the beginning of this time, right? And then the problem is solved. Okay, so because you will not send suddenly from here, right? This is impossible. Okay, so this is not collision. This is collision, right? And if you're sending this slot, this not collision. Okay, so that will be much better. You only have this case. Half the case you will collide. Here you will have twice the collide probability. Okay. So that's what the next protocol, I think. So 2 frame width time is this. Okay, so we can show that the maximum throughput of Aloha protocol is only 18% of the channel capacity, which means if your channel is very wide, right, 100, for example, okay, you can at most, the best case is only utilize 18% of the channel, right? So ideally something like this, right? So here is this is x equal to y. Okay, so this line is x equal to y. Okay, this line. So for example, this is 0.5 and this also 0.5. Right? This is 0.54 because this go beyond a little bit. Okay, so because this is this line, okay? 0.5. 0.5. So what happens here is this is x equal to y. Okay, which means how much load you want to put on the shared media, for example, and how much throughput actually gets out. Ideally, if you put in maybe 0.5, then you get 0.5. This is the idea. But unfortunately, because of the collision, right, Aloha can only guarantee you something like this. Okay, if your load is too high, you almost have no throughput. Okay? And if you load it low, of course, you kind of ideally like this. Right? So this is really thing. Aloha is really for over deployment case. But you can at most have the 18%. Okay, you will not get beyond that. Okay, this is like a 50%. Right? So if you continue, then you're loaded. You actually get less data through. Okay. Yeah, I see a chat. So there's a question from Joe saying that if the sender A and B send at the same time, can't the switch router as the frame to avoid the collision? No, this is not because of the cache, right? So because they are the two hosts are connected to the same medium, okay? And when you want to send, you are sent to this, let's say this is a piece of metal, right? When you put something there, other people will immediately get it, it's light speed, okay? Right, so there's no time to cache, right? Because this is you just think about it in physics, you have the conductance, right? If you put any electric here, here it will run, right? So immediately you put a 1 bit here, this will be 1 bit. Okay? If you also send a 0 bit, right? And if 1 is high signal, right? This will all be 1 bit, right? Something like this. Okay? Maybe finally you also see the 1 bits, right? Like addition of these two signals. Right? Okay. And you will not be able to separate. Okay. Do I answer your question? Yeah, because the thing that you want to cache something, first you need to receive that. Right? So because you cannot receive the correct information, that's why they need to kind of separate them, okay? Like a recover, okay? Because you cannot separate. And the next method, as we said, we can assign some slots, right? You can only send, each host can only send at the beginning of the slot, okay? So that solves the problem a little bit. So it will double. Let me see what my mouse. It will double the throughput. Aloha is 18%. This will be 37%. It's much better. Okay, it's more than 1/3. Okay, and but again, the host must have synchronized clocks, right? If you don't have synchronized clocks, you don't know when is the beginning of the clock where you will start saying. Okay. So again, this protocol we will present a little bit quicker because this is the same as Aloha, but the only difference is that we divided time into slots. You cannot send it in the middle of the slot. Okay, and host may only transmit at the beginning of the slot. That's the only difference. Okay. And here, let me clear this. Okay, here's the example, right? So this is if you don't use any slot, this is pure Aloha we mentioned. If you slotted Aloha, you can see this increases a lot. Okay. So you may be curious why is this the case, right? So how do you compute this? Right? So we can do some simple calculation. Okay, but let's see. Okay, the next one is irrelevant. So let's do some simple calculation. So let's assume we have a bunch of slots. Okay, let me plot things like this. This is a channel. Okay, so you have slots, fixed slots. And now let's assume in this piece of media, okay, they are connected to many hosts, right? And we assume there are, for example, n such hosts. Okay, we have n hosts, right? So, and let's assume that each host will send stuff to the medium with probability P, okay? Again, this is out of your control. Right? This really depends on how people want to send, okay? But let's assume everyone has like maybe 10% of probability to send, etc. Because they have maybe browsing most of the time, but send some new request 10% of the time. Okay, this is P. So in that case, what's the probability that you will successfully send anything, right? So let's consider host one. Okay? The probability that host one will successfully send to a particular slot, let's say this slot, can be computed like this, right? Assuming that different hosts cannot see each other, so their action is totally independent, right? So host one will send with probability P, right? You successfully put on the while, okay? But all the others should not use that slot, right? So the probability that they are not use the slot is 1 minus P, right? Times 1 minus P times 1 minus P, because there are other people with n minus 1 so many, okay? So we'll have this, right? So again, this is for this atomic event in probability theory, right? So host one successfully sent, right? You can also have another atomic event called host two successfully sent, which means host two sent it successfully, and the other 1 minus P host is not sent, right? So you can have, n such cases. So finally we have n times this, right? And given this formula, this is, basically we are saying that, right? So you have n atomic events that a host is successfully sending, right? So this total probability, because those atomic are not overlapping, okay? So you can sum them up, right? And this is the total probability that one host is only one host is sending, right? This is the successful utilization rate, okay? But let's see how we can, so, given different p values, right? This is out of our control. This is really user's decision. But given different p values, we can have different, results out, right? This n is fixed. N is how many hosts. Okay? But how can we compute the optimal? Okay, so we can take, let's say we call this a function of p, right? Okay, and we can take a derivative. Okay, we can take a, let me clean something. Okay. So we can take a derivative f, right? This function f here to the p. Okay, and such that this is saying, hey, if you remember, we previously described, right? If the slope is 0, this is probably the highest utilization rate. Okay, we want to see what is the p and what is the highest utilization rate. Okay, in the previous case. Right. So if you do this, you take derivative, right? So we know that taking derivative to p, the n is a p in there, right? So you just take derivative this and then, right? So and how to take a derivative for this, right? Let's just think about this. Okay, so you first you use this formula fx gx, right? Take derivatives f prime x times gx and fx times g prime x. Okay, using that formula, you will be able to compute the result. Let me see a chat. No, it's not PD, right? So you are using, for example, if you have fx gx, right? You want to take this guy's derivative, right? So this is a basic calculus, okay, right? So the result will be something like f prime f derivative x dx, right? Plus fx g prime x. Right? This is basic calculus, okay? If you take a derivative x, this is, okay? And let me see. Yeah, so here the reason you cannot make out what I'm written is because I didn't tell you, right? So you think about the fx is p, right? Right, and you think about the second part, okay? The gx is 1 minus p and minus p, okay? Then you can put into the formula, right? So you know that what is f prime x, right? Okay, let me use it. F prime x. F prime x is the p to the derivative p is 1, okay? Times gx, right? Gx is what? Just copy it here, okay? 1 minus p to the power n minus 1, okay? I think it's a little bit. So the second part, right? So this is fx, right? Fx is p, okay? So then you should plus second term, which is P times something. The second part is G product. So how to take a derivative of this thing? So you know to the power of something is you just put it here, n minus 1. Okay. And then you take a 1 minus P to the power of n minus 2. So times 1 minus P n minus 2. Okay. But by doing that, you're assuming a chain rule, right? So thinking this is U. Then finally, you also need to take a U to P, right? So if you take U to P, it will be negative. So because it's a coefficient, right? You have a negative sign here instead of plus. Previously we said the plus. Instead of plus, you have a minus. Okay, you will have a minus. So put simply, I think there's a question. Yeah, so there may not be a proof written in the book. I didn't remember exactly, but you can watch the video anyway. Right? So this is the first part, okay, minus the second part, okay. And there's a book, there's a proof in the textbook for, I think, of top-down approach that I referred to. Okay, that I remember that. So again, this is just to help you memorize why this is 18%, this is 37%. I'm proving this. Okay, this is slotted. Okay. Just to help you to strengthen your memory. Okay. So if you remember, we want to set this to 0. Right? So if you set this to 0, which means A minus B equal to 0, which means you want A equal to B. Okay. Then you compute which P will make you the highest. Right. So you know this 1 minus P, n minus 1 cancels. That cancels. But this cancels because you divide 1 minus 1 again, you divide it by 1 minus P. Right? So we should divide this by 1 minus P. Okay. I hope you can follow, which means we cancel this part a little bit. Okay. This is canceled. Okay. The left hand side only 1. Okay. And we can move this up here, then it becomes 1 minus P equal to what? P, let me see, Pn minus P. So here, if you know, this minus P minus P cancels. So finally, what we get is the highest spot. This P should be what? Should be 1 minus n. Okay, because you know this P you divide this n. Okay, and so this is our conclusion, right? So the highest spot is 1 minus n. Okay, so maybe it's easier if we go back to the previous. Okay, so this high spot is you know, if you have, let's say you have 100 users, right? So this highest one is 1 by 1. Because this is reasonable because, you know, if you have 100 people, right? So the probability that you're sending should be only 1%, right? Because the other people are also sending. Right? So if everyone is summing up the workload is 100, that's fine. Right? Beyond that, maybe you will have collision. And then below that, maybe you have some percentage not utilize that one. Okay. But now let's put this number back to the formula, right? So we know P is this, right? And I'm not sure whether you still remember the formula. Let me put it again. So this is n times P, right? And 1 minus P to power, which means 1 is sending the other n minus 1 minus n. Okay. Now you can put 1 minus n there, right? So which means you can cancel this. This is n times 1 minus n. Okay. And this is 1 minus n. Okay. This 1 minus n. Right. And this thing actually monotonically increase. Okay, so if you know, if you take a limit, okay, n to the infinity, this will gradually. This is a rounded, you know, this is so how to say this? This is around 1 by e. Okay, so you can prove that if you know the limitation in mathematics. Okay, so this minus 1 can actually be ignored as n goes to very big, right? A lot of e. But you know, if this is plus, you're limited e. Right? If this is minus, okay, you're limited 1 by e. I think in calculus maybe you learn this, right? So that's why, you know, the utilization really 1 by e. Okay, And if you compute 1 by E is like a 2.78 or something. I don't remember the details. Okay, close to 1/3. Okay, close to 3. So this is larger than 1/3. Okay, that's how you get this. Right. So that's some analysis to help you memorize it a little bit. Okay, and you can rewatch this video to understand it better. Okay. All right, so that's a simple analysis. Next, let's look at the previous Aloha is really for radio network, right? And the propagation is very slow because it's in the air, right? If we are using Ethernet, then it's light speed. Okay, it's almost, when we say almost, because there's still some tricks, right? You have a relatively large data frame size. Okay, so Ethernet is using is something like this. Okay, it's now wide connection. Okay, we have a preamble of 7 bits, right? And we said this preamble should be very descriptive. It's 10 10 10, right? So you don't have long zeros or long ones. Okay, and you have 7 bytes of this, right? Okay, and then you have a start frame. Start frame is a little bit from here where last bit is 1. Then you know, hey, this is not a preamble anymore. It's starting. Okay, then I start to read content. Okay, I mean the host will start to read the content. If it's a shared media, right? Every host will start with. But maybe we find, hey, the destination not me. I will ignore that. Okay. So as we said, there's a MAC address in the link layer, right? Every macro interface card has a MAC address. Okay. So if the MAC address of destination is me, I will get the data to the upper level. Okay. Otherwise, I will just drop it because it's a shared media. Okay. And I will also deliver the source device information to the upper level. So later I can respond to it. And an extreme case is where you use broadcast, right? FFFFF, okay, all 1 bits, right? If that is the case, then if the destination is all F, okay, then I will always get this packet up, okay, get this frame up, because this is broadcasting. Everyone will get this data, okay, and then you will have the length of the data and the actual data, okay, and then you will have some pad and do a checksum, okay. It may be a little bit confusing why we need some pad, right? This is like padding some zeros because you have a let, right? You know it stopped here. This content doesn't matter at all. But we have a requirement, the minimum packet length is 64 bytes, okay? We will see why this is the case, right? So even if, even though, this is using the shared medium, okay? We still want to make sure the other party will receive it, right? So there's still some propagation delay. Previously, in the wireless case, the other side may not receive it at all, okay, right, because of the signal is too weak. But in the Ethernet, the other party will get it, but it could be some delay. Even its light speed, they're still very small, okay. And in order to let the other party get it, right, so can sense it, okay, you need a minimum packet size. It cannot be smaller. So you need to pack something to make sure you at least has 64 bytes, okay. So that's the idea. And I think we will stop here. Let me see the time. Okay. And we'll continue next time, okay, on Friday. Yeah, let's take attendance and then we will continue on Friday and finish this one. Hopefully, okay, if we don't finish, we will also use next time. Okay, let me pull out the attendance. Again, so we have a assignment due, right? So this assignment, we have some filling questions. Okay, so if you have correct answer, right, but you add a unit or you kind of mix them together, right? So there's some fractional number that you mix them 1 number, right? So in that case, you can argue for points with the TA. The TA will give you another 10. Okay. But we will check whether this is really the case. Okay, you can claim, and then if we find this is really the case, we will give you another 10. Okay, we will sample some. Steven, are you here? Steven? Steven? Got it. Okay. Caleb, are you here? Caleb Edward.
I'm here.
Okay. Jacob? Jacob? Jacob, Alice. I see a chat. Okay, I see. Michael Hunt. Michael Hunt.
Yeah, I'm here.
Okay. Jackson. Hi. Are you here? Oh, so I didn't share the tenants list. Just let me make sure I share. Jackson, hi. Are you here? Jackson? No? Andrew, are you here? Andrew.
Here.
Okay. I see a chat.
Professor, did you say Jack Sanchez or Jackson?
Jackson. I think this is not you.
Oh, Jackson, man. Okay, no, that's something.
Yeah. Can you see in the screen? Yeah. Okay. We have another Jackson. So Jackson, man, are you here?
Yeah, I'm here.
Okay, good. Nicholas, are you here? Nicholas? No. Preet, are you here?
Here.
Okay, I see a comment. Okay. Yeah, let's go to the next list. I think so 334 is finished. If you have no question, feel free to do. Okay, I will finish this list. Okay. Megan, are you here? Megan?
Yes, I'm here.
Okay. Matthew, are you here?
I'm here.
Okay. Taisa, are you here?
Tiesha,
Kiesha.
I'm here.
Okay, sorry for the pronunciation. And Hanchao Li, are you here?
Here.
Okay. Clark Ren, are you here?
Here.
France Ren, are you here?
Here, I'm here.
Joshua Taylor, are you here?
Here.
Okay, so that's for today. Okay, thank you. And I will release a video. I see a question. So Clark Ren, you can't see all the content. Some of the poster slides. Let me see, slide 41. Yeah, feel free to leave if you have no question. I'm answering a student question. Okay. Let me double check. I think maybe I updated a little bit, so it's a little bit different. Let me see. So slide 41 on. Okay, Francis, I didn't sample you, so it should be fine. Okay, and okay, let me see. Maybe I can see it here. So let me go to syllabus. One. So we can see what we are seeing. So we are talking about page 41, right? So let me find the message. 41. Oh yeah, so you cannot see it because I think you didn't download it. Okay, so I understand this is blocked, but if you download it, for example, if you this is a PPT file, so you can play it. If you don't play it, basically, so we are sharing the PPT, not PDF. So you can play it to see the details. Okay, or if you want to see the details, you can delete this this image. Okay, it's a PPT file. You can edit it. Okay. Clark, do I answer your question?
Yeah, I get it now. Thanks.
Okay, yeah. So there's another question about the lab, right? So one student want to see a WebSocket. We will consider that. Maybe originally we have another lab which is a proxy. Okay, we probably will redesign it a little bit according to the preference of the student. Okay, and we will see that the latter part. And undergraduates only need 1 lab, by the way. Okay, if you want some bonus point, we can do that. Okay. Any other questions? I think I answered all the questions here. Let me see. Okay, so I think I do not see new questions, but feel free to send me email. Okay, I will answer accordingly. And also, because today is the last day for the math quiz. Okay, if you find any issues with the marking, just contact TA. We will give you another attempt if that's because of the string matching issue. Okay, for the correct answer. Well, have a nice day.